Hello everyone, welcome to another video. This is SOC Level 2 rooms and we are today doing detection engineering. This is the introduction to detection engineering, introduce the concept of detection engineering and the framework used towards crafting effective threat detection strategies, right? So let's move on with the task 1. So detection engineering is an important role and task for a security analyst. It involves developing processes that will guide you as an analyst to identify threats, detect them through rules and processes, and fine-tune the processes as the landscape changes. Now, the learning objectives are understand what detection engineering is, understand the detection engineering lifecycle, and identify various frameworks using detection engineering. And what is detection engineering? Cybersecurity is growing and evolving at a rapid rate, right? Compounded by the progress made in technology. With these adversaries, actions are also evolving. Cyber attacks are becoming so rampant and sophisticated, right? And that it is difficult to keep up with them. Additionally, security teams must develop and adapt to new mindset and practices that will aid them in keeping up with adversaries. That's where detection engineering comes in. Detection engineering is the continuous process of building, operating threat intelligence analytics to identify potential malicious activities or misconfiguration that may affect your environment. It requires a cultural shift with the alignment of all security team and management to build effective threat-rich defense system. Detection types. Threat detection can be viewed from two perspectives, each comprising two categories. First one is environmental-based detection, focuses on looking at the change in an environment-based configuration. So the change in an environment based on configuration, and then the baseline activities that have been defined. With this detection, we have configuration detection and modeling. In the second perspective, threat-based detection focus on element associated with adversaries activity, such as tactic, tools, and artifacts that would identify their action. Under this, we have indicator and threat behavior detection. Now, configuration detection. Under this detection, we use current knowledge of the known environment and infrastructure to identify misalignments. Configuration can cross domain, including network, assets, and identity. Configuration detection has the following benefits and challenges. Benefits: the easiest form of detection to create or maintain in static environment. The challenge is it is difficult to maintain in dynamic environment. Under perfect conditions and coverage, it detects all malicious activity. That is benefit, but limited visibility reduce effectiveness. Individual with different expertise can execute the detection. There is an assumption of knowledge of working infrastructure and configuration for effectiveness. Easy to combine with other detection or forensic response. Frequent configuration change can result in high false positive. That is configuration detection. Next is modeling. A threat detection under this type is done by defining baseline operations and activities and recording any deviation that occur. The primary assumption of this approach is that malicious activity can be sufficiently identified from uh, planning activity, right? And the approach involved building an asset or activity profile that include baseline activities, uh, baseline events, time, and data threshold. An in-depth look into baselining shall be discussed in the next task. So the benefits are used to identify unknown adversaries, activity due to model change, and node threat characteristics. And the challenge is provide no context of threat activity during investigation. Easy to maintain in very static environment, difficult to maintain in dynamic environment. There is challenge. We saw that in the configuration detection, there was challenge with the dynamic environment, and same as in the modeling. Limited visibility, reduced effectiveness, that was with the configuration, as well as human depth knowledge of the, yes, it was there, and potentially add existing malicious activity into the model. Then we have indicator detection. As a reminder, indicators are pieces of information that identify a state and context of an element or entity. There are both good indicators used to identify legitimate activities or resources, such as those used in whitelist, and bad indicators used for suspicious or malicious resources, such as blacklist or malware IPs. Now, IoCs are commonly referenced and derived from investigation against malicious activities or events. By observing threat activities and investigation, analysts can use identify indicator to craft detection and adapt them based on adversaries' rate of change. The benefit is fastest detection to create and deploy. The value of detection depend on the adversary rate of change. Indicators Raise specific threat context. Retroactive in nature, one needs to observe indicator first. Useful for enriching data sources and detection, limited to some indicator that can be processed at a time. Practical for scoping environment post investigation of indicators. Unknown indicator expiry or change timelines can lead to false detection. A lot of information. Then we have threat behavior detection. Analyst will look at an adversary TTPs, that is tactic, technique, and procedure to conduct an attack regardless of any specific indicator. This makes detection more scalable beyond indicators. Through this detection, analysts can focus their effort more efficiently on responding to the threat and mitigate against it instead of utilizing time and resources to understand how and why alerts were triggered. Additionally, threat behavior detection can be paired with established workflows and playbook to provide best practices that can be followed during an investigation. Withstand with the adversary rate of change. Due to adversary complexity, a lot of data is required to provide complete coverage. Easy to tune and adapt to different environment, moderately difficult to make initial implementation due to baseline assessment. Low rate of false positive only detects similar threat behavior based on set analytics. Integrate with defensive playbook, automated remediation plan, modification must be made if detection must be reused. So this is an room with a lot of theory part and a lot of information. I don't think we have anything practical in this room. Then we have this detection as code. The detection as code is structured approach to writing detection by incorporating software engineering best practice principles. This means that detection engineers and analysts will handle detection process and logic as code, offering scalability to address the rapidly changing environment and adversaries capability. Detection as code offer code-driven workflow that create fine-tuned detection processes that introduce critical element found in continuous integration, continuous development workflow. The version control, most SIEM and EDR products lack the ability to track changes made to alert and their definition. By introducing version control, detection rules and processes can be quickly reviewed, tested, and accounted for, enabling higher quality detections. Automation workflow. By adopting CI/CD workflow, detection tests can be automated and allow quick transition and production delivery. With the detection as a code, provide the following benefit: customizable, flexible detection, test-driven development, team collaboration, code reusability, right? So observe a malicious behavior, model it in code, write test cases, commit to version control, deploy it to staging and test, deploy it to production, tune and update. Which detection type focuses on misalignment with the current infrastructure? So that is going to be the first one. Configuration. Which detection approach involved building an asset or activity baseline profile for detection? So that would be modeling. Which type detection integrate with defensive playbook? So that's obviously the last one, I think. Sorry. With the playbook, right? Threat behavior, second last. Now, task 3 is detection engineering methodologies, detection gap analysis. The first step involves looking at the environment and identifying key areas where organizations can improve threat detection. This process is also known as threat modeling and can be done in the following way: reactive and proactive. Reactive, assessing the most recent internal incident report, taking note of the lesson learned from the attacks and carving out missed area of possible detection. Proactive, using the attack framework and various threat intelligence sources to map out potential area of attack and various TTPs that an adversary against your environment may use. Note, threat modeling in this context differ from the detection type discussed in the previous task. Now the data source, identification and log collection. With information about relevant threat actor TTPs and potential risk the organization may face, sources of relevant data associated with the risk need to be identified. This will determine what logs are currently available that will aid in defining detection against the threats and know which ones are missing and which are necessary. Now, baseline creation. Before using all the collected information about adversaries, their TTPs, and any malicious behavior, security analysts need to know what normal behavior is and set their security baselines. This will be a rolling process and require participation from all departments within an organization. Now, setting up security baseline involve identifying the different type of devices running within an organization based on their operating system, services, and function. Security baselines can be grouped into two categories: high level and technical. The high level sets broad OS independent standards guided by specified security policies, whereas technical consists of OS-based configuration standard outlining different system functions and intended behavior. For example, technical baselines outlining OS hardening policies, network activities, identity and access management, application policies. Now, log collection. Once the baseline and source of internal data have been identified, prioritized, the collection of logs and metadata useful for the threat detection should be done. Depending on the infrastructure setup, a centralized system may aggregate all logs using network sensors for network data and services such as Sysmon to collect host data. Rule writing. Based on the infrastructure setup and SIEM services, detection rule will need to be written and tested against the data sources. A detection rule test for abnormal patterns against logged events. Network traffic would be assessed via Snort rules, while YARA rules would evaluate file data. Check out Snort and YARA rule. Deployment, automation, tuning. Test detection rules must be put into production to be accessed in a live environment. Over time, the detection would need to be modified and updated to account for change in attack vector, patterns, or environment. This improves the quality of detection and encourage viewing detection as an ongoing process. Now, detection engineering framework 1, MITRE attack and CAR frameworks. MITRE is well known for publishing identified CVE that adversaries would look to exploit for their malicious activities. Additionally, MITRE provides knowledge-based access that security analysts can use to track techniques and tactics commonly used by malicious actors across different platforms such as Windows, macOS, Linux, mobile. The attack framework helps map out adversarial action based on infrastructure in use for detection engineering. It guides what to look for, especially as part of the detection gap analysis phase. The CAR, Cyber Analytics Repository knowledge base, is used to detect adversary behavior and prioritize them based on attack framework. This is the screenshot of the MITRE attack framework, in which we have different techniques mentioned, starting from reconnaissance all up to the impact. Now, each technique has several undefined techniques, right? So if you see, we have in reconnaissance, we have active scanning, gather victim host information, and many more. Similarly, for initial access, we have drive-by compromise, external remote service, phishing, valid accounts, right? Now, pyramid of pain. This is well-known framework in the industry and is mainly used to showcase the pain for the adversaries. If the defender detect their TTPs, then how difficult and or costly it would be for the adversaries to change their TTPs. Now, it all starts from hash value, IP address, domain name, network and host artifact, tools and TTPs. So IP address is easy to change, domain name is simple to change, network and host artifacts annoying, tools challenging, and TTPs tough. That is on the top. So cyber kill chain. Thanks to military concept of an attack strategy, Lockheed Martin formulated the cyber kill chain framework to define the necessary steps followed by adversaries. The framework focuses on 7 crucial phases that cyber attack commonly follow, starting from reconnaissance all up to action on objectives. So recon, weaponization, delivery, exploitation, installations, command and control, and as a security analyst, detection and a detection engineer, understanding the cyber kill chain will give you the knowledge to recognize intrusion attempts crafted by an adversary and map them into your detection plan. The unified kill chain was developed to complement the cyber kill chain by combining it with other frameworks, such as MITRE attack framework. This expanded the original kill chain into 18 phases to cover every known element of a cyber attack. So unified cyber kill chain with 18 phases, starting from reconnaissance, weaponization, delivery, social engineering, exploitation, persistence, defense evasion, CNC, pivoting, discovery, privilege escalation, execution, credential access, lateral movement, collection, exfiltration, impact, objective. Which framework looks at how to make it difficult for an adversary to change their approach when detected? Of course, uh, pyramid of pain. What is the improved cyber kill chain framework called? Is unified the unified kill chain. The unified kill chain. How many phases are in the improved kill chain? As we know, it's 18. Now, detection engineering framework 2, alerting and detection strategy framework. Planter developed the ADS framework to provide a guideline for documented detection content. A significant challenge faced by security team and Planter being no exception is alert fatigue and apathy, mainly caused by poor means of developing and implementing detection alert that would result in effective incident response and mitigation. The ADS, Alerting and Detection Strategy Framework, seek to address this challenge, provide a guideline for constructive, effective detection and alert. So ADS framework has a strict flow that detection engineer must follow before publishing detection rules into production. The stage involved are goal, describe the intended reason for setting up alert and the type of behavior that needs to be detected. Categorization, mapping the detection to the MITRE attack framework to provide analysts with information of TTPs for investigation and areas of kill chain where the ADS will be used. A strategy abstract, provide a top-level description of how detection strategy being implemented function by outlining what the alert will look for, the data source, enrichment resource, and the way of reducing false positive. Technical context, describing a technical environment of detection to be used, providing analysts and responders with all the information needed to understand the alert. Security analysts should align this information with the platform and tools for collecting and processing threat alerts. Blind spot and assumptions, describe an issue identified where suspicious activities may not trigger the strategy. Assumption and blind spots help clarify a way ADS may fail or bypassed by an adversary. False positive, outline occurrence where alert may be triggered due to misconfiguration or non-malicious activity within the environment. This makes it easy to configure your SIEM to limit alert generation to only targeted threat when pushed to production. Validation, every detection needs to be verified. And here you can outline all the steps required to produce a true positive event that would trigger the detection alert. Consider this unit test, which can be even be script or scenario used to generate an alert for effective validation. Develop a plan that will produce a true positive outcome, document process of the plan, from the testing environment, test and trigger an alert, validate strategy that triggered the alert. Priority, setting up alert level, which the detection strategy may trigger tagged. This section provides the detail of the criteria used to set up preferences. It is separate from the alerting level shown through the scene. Response, provide detail of how to triage and investigate a detection alert. This information is helpful for analyst and responder to be able to prevent extreme repercussions. So goal, categorization, strategy abstract, technical context, blind spot, false positive validation, provide response. Now we have detection maturity level model. Ryan Stillians brought forward the detection maturity level DML model in 2014 as a way for an organization to access its maturity level concerning its ability to ingest and utilize cyber threat intelligence in detecting adversaries' actions. According to Ryan, uh, there are two guiding principles for this model. An organization maturity level is not measured by its capability of obtaining valuable intelligence, but by its ability to apply it to detection and response. And without established detection function, there is no opportunity to carry out response function. The detection maturity level model comprises 9 dedicated maturity levels numbered from 0 to 8, with the lowest value representing technical aspect of an attack and the highest level representing abstract and intelligence-based aspect of an attack. Now, DML 8 goals, the pinnacle of the model, represent organization that can detect an adversary's motive and goal. Unfortunately, it is nearly impossible to conduct detection solely based on calls, as in most cases. It is a guessing game based on behavior findings from lower DMLs. Now, DML7 strategy followed closely by 8. This level is non-technical, represent the adversary intention strategy to fulfill them. Organization at this level would have a mature intelligence source that will ensure they have context about the adversary plan, which will be helpful to responders. Then we have 6 tactics. Organization must be able to detect tactics being used by an adversary without necessarily knowing which technique or tool they use. Tactics are detectable after observing patterns of event that aggregate over time and condition. 5 techniques. Technique usually are specific for or to an individual or APT. Therefore, adversaries leave behind evidence of their attack habits, behavior, organization that can detect when a particular threat actor is in their environment are at the advantage. 4 procedures. Organization required to detect sequence of events from an adversary at this level. They will be organized and follow a given pattern, such as pre-exfiltration reconnaissance. 3 tools. Detection of tools can fall into 2 phases. The transfer phase, where the tool is downloaded via network onto a host device, reside on a file system or in memory, and in the second, detecting through the tool's functionality and operation. In some cases, this detection level would require organization to perform reverse engineering against adversarial tools, making it difficult to cause havoc by understanding their tools capability. Now, level 2, host and network artifact. Most organization resources would be spent gathering IoCs artifact as threat intel at this level. Unfortunately, in most cases, indicators are observed after the fact. The threat actor would likely be causing havoc within the network when artifacts are picked up and investigated. This has been described as chasing the vapor trail of an artifact. 1, atomic indicator. This level compromise organization utilizing threat intel feed in the form of list of IPs domain to detect threat. 0, none. At the bottom of the modular organization that operate at this level have no detection processes established. So what adversaries want? Level 8 and 7. How adversaries plan to achieve their objectives 6 to 3. And evidence left behind during an attack pursuit of their objective 2 and 1. The last task is detection detective, something interesting. So let's visit the site. It's a scenario. The THM is seeking to establish a detection engineering process to detect changes made to privileged and administrative group and the account in their Active Directory. As a detection analyst, you have been tasked with developing the strategy based on a set of questions. Each question come up with one correct answer. Therefore, it is up to you to identify and select it. You will have 3 attempts to complete the exercise before it reset. Now, use the unusual PowerShell host process EDS framework template below as a guide to what each stage of framework requires. Goal: detect when PowerShell is loaded into the unusual host process. Categorize execution. Let's proceed. Establish a detection engineering process without privileged and administrative account and group in under 3 attempts. What categorization class would you assign to the strategy? Strategy abstract. No. Yes. The last is what would be part of the response. Identify if the application binary corresponds to the installed application. Alert user whenever no. Whatever this would the answer, maybe binary. No. 2 attempts left. Okay. Second favorite would be validate the group modified user added and the user making it. Yes. Here is the CTF, the flag. So finally, this room is completed and it was good learning a lot of information in the single room, like a lot of theory. But it is good to know about different frameworks and go through all those techniques, that how we can monitor adversaries and how to utilize different frameworks to different use cases, especially as an SOC analyst. So that is it for this room, and I will see you in the next one. Thank you.